Thank you. I'm Padon. Thank you for being here. So in this talk, I'm going to explain to you a way to write safety proofs. Which use simpler formulas than if you were to trying to prove safety using just an inductive invariant. And I'm going to do so by leveraging ideas about forward-backward symmetry of safety proofs and a notion of prophecy. So when we're given a safety verification task, we're given the system over some state space, and we have some initial states of the system, some bad states that we do not want the system to reach, and a set of transitions. And specifically in this work, we consider systems specified in first-order logic. So the initial states and the bad states are given using first-order logical formulas, and the transitions are given using a transition formula over two states. And our goal, when given such a safety verification task, is to prove that there is no error trace of the system. So there is no sequence of steps leading from an initial state to a bad state. And the traditional way to do this is to find what we call a safe inductive invariant. So this is an inductive invariant, which means it's another formula which describes a set of states that contains all of the initial states. And if you begin a transition within this inductive invariant, you remain inside this inductive invariant. And it is safe, meaning that it excludes all of the bad states that you do not want to reach. So this is the traditional way to do this. And when we're operating in the setting of first-order logic, then these conditions can be verified using an SMT solver. Now, the problem with using a safe inductive invariant may be that when the systems become complex, the safe inductive invariant becomes complex. So for example, here you have an example of part of the inductive invariant for Paxos, and you can see that it is complex both in terms of the kind of Boolean structure that the formula has. So it has conjunctions and disjunctions, and also, perhaps more importantly, in terms of the quantification. So a lot of quantifiers and quantifier alternations and quantifier nesting. And these two sources of complexity mean that when we are trying to write a safe inductive invariant for this kind of problem, we need to consider a large candidate space for possible invariants. So either manually or using an automatic technique trying to find a safe inductive invariant. And additionally, when we want to check a candidate invariant, we need to perform complex SMT queries that may involve a lot of quantifiers. So the idea in this work is to prove complex properties such as the invariant that I showed you before, but by breaking them down into simpler incremental steps. And specifically, we do this by proposing a proof system for safety, which incorporates two main ideas. So the first idea will be incremental forward-backward reasoning. And I will show that this allows us to use formulas with a simpler Boolean structure. And the second component will be a notion of prophecy, which will result in formulas with a simpler quantifier structure. So let's begin with the forward-backward reasoning. What do I mean by forward-backward reasoning? So let's say we have this kind of safety problem, and before I showed you that we can find perhaps this kind of safe inductive invariant, this is an invariant in the forward direction, right? It's an over-approximation of the reachable states. We could have proven safety equivalently using a backward inductive invariant. So an invariant which includes all of the bad states and is preserved backwards in time. And if this kind of invariant excludes all of the initial states, then the system is safe. But let's say these kinds of invariants are too complex for us to express, and we want to use simpler reasoning, but we allow our proof technique to use incrementality. So let's say, what does it mean that we want to use simpler properties? So let's say we have a formula which is not expressive enough to express exactly the safe inductive invariant that we want to find, but expresses some simpler property which holds on all reachable states. So this is an inductive invariant which is not sufficient for proving safety, but it is simpler to express. So we have not managed to prove safety, but we have excluded some of the bad states, and we can now continue the proof incrementally. So we can now ignore all of the bad states that we have already managed to exclude, and maybe now we can find a backward inductive invariant with respect to the remaining bad states. And now we managed to exclude some of the initial states, effectively proving that these cannot lead to bad states. And maybe now we complete the proof by finding a third simpler formula, which shows that these initial states cannot lead to bad states. So intuitively, why is this proof of safety? Well, you can think about this kind of proof as accumulating properties of error traces, right? In each step, we added either a forward inductive invariant or a backward inductive invariant, which proves the property of error traces. And if we manage to exclude either the bad states or the initial states, then we have managed to prove safety of the system. Well, we can now ask whether if we have this kind of proof, could we just have used an inductive invariant, and what would it look like? And we have a theorem in the paper that shows that if you have a forward-backward proof, there always exists a safe inductive invariant, which is a Boolean combination of the formulas that you use in the forward-backward proof, but this inductive invariant may be more complex. So it may include more conjunctions and disjunctions. So for example, the forward-backward proof that I showed you before, the invariant would look something like this. So you can see that if you were trying to find a safe inductive invariant for the problem, it would have been more complex in terms of its Boolean structure than the incremental proof. Well, and we also show in the paper that there are problems where this simplification is strict. So the forward-backward proof is able to use simpler formulas than the safe inductive invariant that is required to prove safety. Which means that we can sometimes use this technique to simplify the Boolean structure of formulas that we check inductiveness for and that we search for when searching for a proof. Now, of course, we're operating in the setting of Forestall logic, so the obvious question is, can we use this to reduce the kind of quantification in formulas? And the answer is partially. So we saw before the forward-backward proof that resulted in this equivalent safe inductive invariant, which means that, for example, if these formulas were universal formulas, then the resulting inductive invariant would have included 3 quantifiers and one of them an existential quantifier. So if the formulas that we use in the forward-backward proof contain quantification, we may have reduced the number of quantifiers that we need in a formula, in each formula used in the proof. But remember that we can always convert any forward-backward proof into a safe inductive invariant, which is a Boolean combination of the formulas that we use, which means that we cannot ever reduce the kind of quantifier nesting or alternations that we use just by using forward-backward steps. Because otherwise, we would have been able to, because such a formula cannot be broken down into a simpler Boolean structure. So, for example, if we want to prove that all error traces satisfy this property as part of our incremental proof, we cannot hope to do so in several steps. We must do it in one step. So the question is now, what can we use to reduce the quantifier nesting and alternations? And perhaps unsurprisingly, we use ideas from prophecy, a notion of prophecy, to simplify this quantifier structure. So let's look at an example. The main idea is to replace quantification with explicit prophecy witnesses. So let's say you want to prove this kind of property. You want to prove, as part of your incremental proof, that every error trace satisfies this quantified property that says that there exists some x that satisfies p, and for all y, q of x, y holds. Well, maybe you can add some witness symbol, w, and prove in the forward direction that it satisfies p. And then, after adding this kind of witness, you prove in the backward direction a backward inductive invariant that for this w, which satisfies p, the universal property holds that for all y, q of w, y holds. And you have effectively proven the quantified property that for every error trace, there exists some x that satisfies p and the universal property. And you have done so in 2 steps instead of 1, and used fewer quantifiers and fewer quantifier alternations. Now, of course, the question is, when does it sound to do this first step, to add some witness satisfying p? And as an example, consider a situation where you can prove that in every initial state there is some element satisfying p, and that p is a property that is preserved for any element in a transition. In that situation, you can add this kind of assumption about error traces to your proof. And you can ask that question more generally. So when does it sound to add a witness satisfying some property to the properties that you have accumulated about error traces? And in the paper, we characterize this as a safety problem. So as another safety problem that if you prove its safety, this means that you are allowed to add this kind of prophecy. And intuitively, we do so by introducing a monitor relation that keeps track of possible witnesses and making sure that this relation is never empty. And now you can use a separate safety proof to prove that this prophecy is sound, and then you can continue with your incremental proof. Now, in practice, a lot of the times, these kinds of soundness problems have a very particular structure, so we develop heuristics for example, what kind of invariant do you usually need to prove soundness of prophecy, which is what we use in practice in the case study that I will talk about soon. Now the question is, again, we have this kind of incremental proof that uses prophecy and forward-backward iterations. Can we just use a safe inductive invariant? And the answer is yes, but this time this inductive invariant will include more quantifier nesting and alternations. So at a very high level, why this happens is that you have some proof of the soundness of the witness that has some quantifiers, and then you have the remaining incremental proof that contains more quantifiers, and when you construct the inductive invariant for the original problem, you get these quantifiers nested under each other. And this gives you the kind of nesting that we saw before. Very similar to the example that I showed you before. And this similar to forward-backward iterations, this can sometimes be used to reduce the kind of quantifier nesting and alternations that you need to use in formulas. So this culminates in a proof system for safety problems where every statement is a safety problem, and we have rules for introducing inductive invariants, for performing incrementality, and for introducing prophecy, where you see in the prophecy rule, for example, you need to prove the soundness of the prophecy and continue the incremental proof in the other premise. And the rule for time reversal to take advantage of the forward-backward symmetry. And we show in the paper, as I showed you here, that this kind of proof using these rules can be converted into a safe inductive invariant for the original problem, but that using more rules means that you will get a more complex safe inductive invariant using the construction that I showed you before. Okay. We have implemented a proof checker for this system in the MyPyV tool. So instead of writing like a proof tree that looks something like this, you can write the forward-backward iterations and introducing the prophecy in something that looks more like this. And we constructed manual proofs for 12 Paxos variants and Raft. And we compared the three possible proof methods for these variants. So the first method is just the forward inductive invariant that is used to prove safety, the traditional method, and then a proof system that only uses forward-backward iterations, a proof system and then the complete proof system that also uses prophecy. And we compare the kind of formula complexity that you need to use in order to prove safety for each of these proof systems. So I'm not going to go over the full case study, but here's some illustrative examples. So the proof for Paxos includes an invariant that looks something like this. So it has these quantifiers and quantifier nesting and alternations, and also a Boolean structure that contains both conjunctions and negations and disjunctions. And if you try to prove the same example using forward, backwards, and prophecy, then you can replace this kind of invariant with witnesses for some of the quantified variables. Of course, you need to prove the soundness of adding these witnesses using some more formulas. And then you can do a backward iteration with a simpler formula and a forward iteration with a simpler formula. And you can see that, and this effectively replaces this kind of invariant in the proof of safety for this example. And you can see that the formulas that we had to use, that the user had to provide in order to complete the proof, are much simpler. They contain only universal quantification and are clausal in form. And I refer to the paper for the full case study. So to conclude, I presented the proof system for incremental safety proofs, which incorporates both forward-backward reasoning. This allowed us to simplify the kind of Boolean structure in formulas, and prophecy and soundness, and prophecy and the soundness formalization characterization of when is it sound to add prophecy, which allowed us to simplify the quantifier structure in formulas. And we saw that adding more using more proof rules means that the formulas that you have to use in proofs become simpler. we have implemented this in a proof checker and conducted a case study. And we think that one of the most interesting directions for future research is to try to automate proof search in the system. And hopefully, because we need simpler formulas, this will mean that automation will find proofs faster or more easily. So thank you, and I'm happy to take any questions that you might have.
We got time for questions.
So I know prophecy variables from simplifying proofs in distributed systems and concurrency in general. And there usually what happens is that you don't know whether some event is going to happen in the future, and so you by having a prophecy variable that predicts whether it'll happen or not, what usually happens is that you have these two distinct scenarios about the future, whether the linearizability point is going to be now or later or something like that. You can decide based on the future, right? But I get a sense that this is not the sense in which your prophecy variables are. So is this a more general notion of a prophecy variable, or can you describe what intuitively a prophecy variable, why does it simplify a proof?
Yeah, so the name prophecy here may be slightly confusing. So this is a kind of prophecy. It can also, in some contexts, be a kind of combination of history and prophecy. So this kind of prophecy doesn't necessarily talk about something that is decided in the future, maybe. Basically, it allows you to talk about the kind of things that have to happen on an error trace. So, for example, if you have a distributed protocol that some decision happens at some point, and your invariant would usually say something like, maybe there exists some quorum where this decision was accepted, then your witness for this quorum will witness this, will be the one that performed this decision. So in that sense, it's something that happens in the future, but it's a bit our formalization. If you return to our formalization of how we introduce witnesses, we say that we have this characterization that proves that the witness that there is a witness for every error trace that satisfies this property. So this is the kind of requirement for the prophecy. But this is the only requirement. So maybe this witness is in the first step, or maybe it's in the 100th step. But all we prove is that on every error trace there is this witness. So it can happen at any point in the trace. Yeah.
So it looks very different from the ones.
Yes, it has similarities and differences. I think that it's not a generalization, but it has intersections with other notions of prophecy. Yes.
Thank you.
Okay, great. We still have time for another question. Okay, so I have a question about this future work direction. So, you have more proof rules here, right? But is there some sense in which the simplification of the individual proofs is amenable to proof search? Have you experimented with this at all?
Yes. So, as you say, now we have simplified the kind of formulas that we need, but we have complicated the proofs in terms of the structure that they may have.
Yeah.
So we have in mind a form of proof automation which we think works well for the forward-backward part. So you can think about just performing forward iterations and backward iterations, alternating these if you just have forward-backward steps. And we have good intuitions as to why this will be a good tactic for proof search. Mm-hmm. The real difficulty is to know when to introduce prophecy. What kind of prophecy do you need to introduce? And this is harder to automate, and yeah, so this is the main challenge when you want to automate this kind of thing.
Do you feel like as you did case studies with this that you developed intuitions for how to come up with those prophecies?
Yeah, so we have good intuitions as to what kind of prophecy we need to introduce for these examples, but of course we don't know how well this generalizes for other examples. Yeah. The forward-backward automation seems to general as well, because just basic observations about the kind of formulas that you need. But yeah.
Okay. Great. Let's give the speaker another round of applause.